So with that, I would like to introduce our first speaker, Professor Longju from MIT. Today, his lecture will be about electron correlation and topology in crystalline graphene. Will everybody please join me in welcoming Longju to the stage?
Okay, good morning. Thanks for organizing this very nice summer school. I look forward to interact with the speakers and the students in the audience. Hopefully I can learn something that I'm not so familiar with. So I'm going to give you two talks this morning. This is the first one. And both talks will be around the topic of electron correlation and topology in crystalline graphene. I emphasize crystalline because there has been a lot of efforts going on in the twisted form of graphene by introducing some magic angle between the layers of carbon, and many amazing things have happened. Well, what I want to tell you today is that even without the twist, in the simplest form of graphite, you can possibly find that nature gives us, there are still many things we do not understand. Okay, so before I get started, these are the people who contribute to the work I'm going to share with you. These are my students and postdoc at MIT, and we enjoy the benefit of collaborating with our theorists, Santiu and Liangfu at MIT. And some of the early transport work were done in Professor Hong Kong Park's group at Harvard. And we have collaboration with these people down here from Berkeley and China and Japan through the course of this journey. Okay, so both topics I want to talk about, electron correlation and topology, drive emergent quantum phenomena in condensed matter physics. And since I'm at Princeton, I like to mention this idea Philip Anderson put up: more is different. When you put many identical elementary particles together, the interaction between them could result in totally different and surprising results. If you think about, we usually deal with crystals that has the astronomical number of particles in them, and there are a lot of defects and disorders. But when you put them together, these very important physical principles of electron correlation and topology drive some very robust macroscopic scale phenomenon that you can measure. For example, superconductor is a great example where the electron correlation will give you perfect zero resistance in the form of Cooper pairs. And the principle of topology has led us to discover many topological phases of matters, especially here at Princeton. You must be very familiar with the quantum Hall effect, fractional quantum Hall effect, that give you precisely quantized the Hall resistance that's proportional to fundamental units of h over e squared times 1 over an integer of fractions. And the general law that we can learn from the study of correlation and topology in the history of condensed matter physics, in my view, there are two things, right? One is that you want to get some flat electronic band. So the kinetic energy of the electrons is dwarfed by the energy scale characterizing the interactions between electrons. And that's usually when something beyond the single particle physics is likely to happen, right? You want to have flat band that has large density states. And on the other hand, okay, one more word. You want the bandwidth of your electronic band to be small, or comparable at least, to the energy scale of the electron interactions. And if you want to find a topological phenomenon, one way of thinking about it is that there's this very old concept in condensed matter physics, in terms of describing the electron motion in a crystal. Not only you need to consider the group velocity, which you can get from the energy dispersion, you also need to consider this so-called Barry curvature effect, which drives an anomalous velocity. And you can integrate this anomalous velocity over the whole Brillouin zone, and you can get some integer called Chern number, and that characterizes the topology of the band. So these are the ingredients that we need to look for correlation and topological phenomena in solid state systems. And it has been a very long time to find these key ingredients in crystals, okay, atomic crystals. For example, bisco is a very well-known high-temperature superconductor material. And through the engineering of very robust, reliable crystal lattice, you can get flat band and strong correlation, and give you amazing discovery of superconducting transition temperature that's well above liquid nitrogen temperature. On the other hand, you can also grow atomic crystals in the Z direction by forming some heterostructures, and you subject it to a high magnetic field to induce the so-called lambda levels. And many amazing things happen in the lambda levels of such kind of heterostructures of atomic crystals. In the more recent years, in the field that I work in, called the two-dimensional materials, people have realized this is another platform that gives you a lot of flexibilities in engineering the structure and subsequently the physics. Basically, two-dimensional materials are atomically thin, and they are like papers. There's no chemical bonding between the layers, which means you can choose to make such a structure by choosing how many layers to stack on top of each other through the van der Waals interaction. And you can choose what these layers are, because there are so many species of two-dimensional materials with different property, like metal, semiconductor, insulator, magnet, superconductor. And you can also control how you stack them together by introducing, for example, a twisted angle between the layers. And you are still at the two-dimensional limit, which means after the structure is made, you can use something called the gate electrode to institutionally tune the property of your stack to reach different corner of the phase space and see what happens. So this platform has been enormously successful in the past few years, especially in the form of the so-called Moiré superlattice, which is a very general concept. When you stack two layers of 2D material on top of each other, they have the same lattice structure, but they have possibly different lattice constant. For example, between graphene and HBN. So in this case, even if you're at the 0-degree twisting angle, you're going to get a spatial beating pattern that is roughly on the order of 10 nanometer, which is much bigger than the atomic scale. And that gives you additional knob to control both the key parameters. One is the bandwidth, which characterizes the kinetic energy of the electron, W, and the other is how the electrons interact with each other. For example, when you put two of them at the same Moiré period site. Of course, even if you don't have the lattice mismatch between the two materials, for example, you grab a monolayer graphene and another monolayer graphene, you can still generate a Moiré pattern by introducing a twist angle between the two layers. And then you also get tunable periodical structures, and that generates a potential that can control the electrons further. And in the past few years, this idea of Moiré superlattice between two-dimensional material has resulted in many amazing phenomena. The first one is pioneered by my colleague Pablo at MIT, where they find at some magic angle between two layers of carbon, you're going to get superconductivity and the phase transition to some correlated insulator, likely molten insulator, and other phases that can be tuned just by using a gate voltage, which is very convenient. It's like you put materials with disparate properties in the same material, and you can switch between them very conveniently. And after that, there are other two-dimensional Moiré superlattices formed between, for example, ABC trilayer graphene, HBN, due to the lattice mismatch. And there's also works on Moiré superlattice between two layers of semiconductor two-dimensional materials like transition metal dichalcogenide. And a wide range of phenomena from multi-insulator, superconductor, orbital ferromagnetism, even quantum anomalous Hall effect have been discovered in this material system. So I was enlightened by both of these two wisdoms, right? One is from the conventional condensed matter physics study that you get crystals, which is very reliable, very repeatable, and very robust. However, it suffers from the issue of once you make the material, the structure is fixed, there's very little thing you can tune in situ. While two-dimensional materials, or the stacks of them, enjoy the benefit of extremely rich structures you can engineer, you can design and realize them. However, sometimes you suffer from the inhomogeneity of the twist angle, which subsequently affect the properties a lot. For example, as you can see in this image here, this is taken by the so-called scanning nanosquid by Elie Zeldov's group at the Weizmann Institute. The twisted bilayer graphene made by Pablo's group has a lot of variation in the twisting angle at the microscopic scale. So the sample is expected to be an ensemble of different patches with different properties. And a lot of good property may get smeared out due to such kind of inhomogeneity. So I was enlightened by both of them. I want to combine these two wisdom to develop something that take advantage of both of them. Okay, I'm going to start with some 2D crystals. Okay, so it enjoy the benefits of chemistry. And I'm going to make it more interesting by proximatizing these 2D crystals by some other two-dimensional materials by taking the advantage of the van der Waals stacks. For example, spin-orbital coupling and Moiré effect from the proximatized layers. And in this combination system, I'm going to control the single particle energy and the electron interaction energy, and hopefully I can drive the correlation and the correlation-induced topology in such system. So with this as a background, let me show you the outline of my talks today. In the first talk, I'm going to share with you the material we're going to use, which is a crystalline multilayer graphene in the so-called rhombohedral stacking order. And I will talk about several observations we made based on this crystalline graphene in the absence of any Moiré effects. And then in my second session, I'm going to talk about effects when you introduce a Moiré, and that happens only when you introduce a Moiré superlattice. And I'll be focusing on fractional Chern-Insulators and fractional quantum anomalous Hall effect. Okay, so let's go with the first one where there's no Moiré, there's no twisting, there's no Moiré between graphene and graphene, there's no Moiré between graphene and HBN. It's pretty much just a crystal. Okay, so I think it's fair to say, even in 2024, after 2 decades of heavy studying of seemingly the very simple material called graphene, which is composed of just carbon atoms, we still do not really understand what even the simplest form of a graphite crystal can deliver. If you use tape to exfoliate graphene out of graphite crystals, and you put it on such kind of substrate, and you look at it with an optical microscope, you get randomly different regions with different contrast, and the contrast tell you the number of layers of carbon you have there. Well, it turns out the graphene structure is much more rich than just having different layer numbers, because if you zoom in to this red box here, the majority of this box has uniform color, and that makes you think, oh, this is a homogeneous region. And if you count the contrast, you find out it's 5 layers thick. Well, it turns out there are internal structures within that 5-layer region that have bright and dark contrast. And those contrasts can only be revealed if you use photons with much lower energy than the visible photons you have in your optical microscope, because lower energy photons are more sensitive to the subtle difference in the electronic band structure for different stacking orders. These two contrasts here correspond to the so-called Bernal stacking and the rhombohedral stacking of graphene. They both exist in graphite. Bernal stacking corresponds to the so-called AB, AB, AB stacking, where you take alternate positions when you stack layers on top of each other. This is the most stable form of graphite, and about 80% of the volume of graphite will be in this Bernal stacking. And the darker region here corresponds to the so-called rhombohedral stacking, which is corresponding to this kind of staircase like ABC, ABC, ABC stacking. So you keep shifting the layers as you stack more and more of them on top of each other. And the rhombohedral stacking order is metastable. It is, although a local minimum in energy in terms of a structure parameter, but it's not as stable as Bernal stacking. However, this relatively less stable stacking order of rhombohedral give you potential of electron correlation and topology for the following reasons. Okay, this is rhombohedral stacked graphene multilayers, and most of, if you want to guess how the energy band structure of this material look like, there's a very simple way of looking at it. Okay, you take two atoms from each unit cell and you stack them on top of each other like this staircase. Most of the electrons from orbitals in the middle will hybridize very strongly, and they will push themselves away from zero energy. Only two electrons kind of coming from these two dangling bonds, A1 and Bn, will remain degenerate at zero energy. And of course, if you introduce more and more unit cells, you get a crystal instead of a big molecular. You're going to get energy dispersion. But the key point is that you have a pair of bands coming from these two orbitals that is relevant at zero energy. And they follow a very interesting energy momentum dispersion relation that is energy proportional to momentum to the nth order, where n is the layer number. And this is just because in order for these two electrons to talk to each other, they have to hop through all the intermediate layers in between. And they will get, as the layer gets thicker and thicker, this become more and more indirect. So this dispersion become more and more flat. So let's think about if you have n equals 1, which is the simplest case of monomer graphene, you get a famous linear Dirac cone that has a big Fermi velocity. But when you start to crank up the number of layers from 2 to 3, 4, 5, very soon, these two bands that remain degenerate at zero energy will become more and more and more flat. And that's what we want for promoting electron correlation effect, because you have large density states here. So I would call this kind of flat band as the pristine flat band you got from just the right part of the graphite. You don't even need gating. Of course, you don't need twisting or moire. And this structure has another advantage of gate tunability. If you apply a vertical electric field by applying the gate voltage, you can break the degeneracy between A1 and the Bn here, and that potential energy difference will correspond to a band gap opened here at around zero energy. So you get the tunable semiconductors by just applying electric field, and that gap will further squeeze the bottom of the conduction band, for example, and make the density states even bigger than at 0D. So you also get gate-induced flat band. So this is half of the story. Half of the ingredients we want, right? We got flat band, and it's tunable. On the other hand, such kind of band structure is also good for the search of topology, because the band crossing points are topological objects. If you have a monolayer graphene, the Dirac point carries a barrier phase of pi per valley per spin. Well, if it's 5 layer in the rhombohedral stacking order, it's simply 5 pi, 5 times bigger than the monolayer graphene. And when you apply a gate electric field to open up the gap, you also got the chance to tune the distribution of barrier curvature of states in these states near the band gap. For example, there are two valleys in the graphene lattice, so-called K and K prime valley. They are time reversal pairs of each other. If you fix the gate electric field, the two valleys, they will have opposite barrier curvature in the same band, because they are time reversal pairs. They have to cancel each other. And if you focus at a specific valley and tune your electric field continuously, you can close the band gap by go to E equals 0 and reopen the band gap in the opposite way. So you are kind of like swapping the conduction of valence band here. So you also control the barrier curvature, the sign of the barrier curvature of these bands through this topological phase transition, if you just look at one value. So we have also potential for quantum geometric effect and topological effect. Experimentally, once you have this barrier curvature, as we said, it would drive the anomalous velocity that can be directly measured in your experiment. For example, you just measure the Hall conductivity or the Hall resistance by integrating all the contributions from the occupied electron state, and you'll be able to get a non-zero value of the Hall signal if the time versus symmetry between k and k prime is broken. On the other hand, there's another effect that's associated with this barrier curvature distribution. You can think of the electron wave packet will rotate around the center of itself, and that would generate an orbital current loop that give you magnetism. And this is a very different form of magnetism from the spin-driven magnetism, because this is ultimately coming from the orbital motion. So I hope I have convinced you, just based on this very simple tight banding calculation, that rhombohedral stacked multilayer graphene is a good place to look for flat band and topological physics. So if you manage to make a device where rhombohedral graphene, say 5 layers, is the core, and you have top gate and bottom gate here, then you are ready to explore what this material really gives you and whether there is correlation topology effect. So you can tune the top and bottom gate voltage to control the charge density and the gate electric field or displacement field independently. 2 knobs for 2 parameters. So what we did first is to grab such a Hall bar device and measure the resistance as a function of charge density and the gate displacement field. What we would expect to see if nothing interesting happened or everything is described by single particle physics is a very simple behavior where you get the band gap open the semiconductor, and by doping charges into it, you make it more and more conducting. Well, what we actually got from experiment is very different from that. For example, if you look at charge density equals 0 and displacement field equals 0, this point here, you would expect a very good metal because there's a lot of density states. It should be a good metal, but in fact, the experiment tell you it's a very, very good insulator. So this is already a signature telling you that electron correlation has kept out the band structure because it's so flat. On the other hand, you can go different directions, right? You can keep at charge neutrality and increase the displacement field. You'll go from this correlated insulator to some metal state, and then to another insulator. And this insulator is likely the gap open, the semiconductor, the single particle band insulator. Well, you can also go the other direction by adding charges into it, and you got the regions with all kinds of shapes and boundaries, different contrasts, and those are also correlation effect to tell you either the spin or the valley degeneracy is broken, or a combination of them is broken due to the exchange interactions. So this is the first glance. And I am going to tell you more specifically some of those states in the next session here. But I hope I have convinced you that without moire, without twisting, the crystalline form of graphite is already quite rich to look at. Okay? As I said, you have all these different regions, seems to have different resistance and boundary between them. What are these ground states? To figure out what they are, there are 2 things that you can do. One is to figure out the degeneracy at the Fermi level, right? There's 2 spin, 2 valley, and in total there should be 4 combination of them. So there should be 4 copies of the same band structure that are degenerate if nothing interesting happens. But when correlation effect happens, those degeneracy could be broken. So the first thing you can do is to apply an outer plane magnetic field to induce quantum oscillations driven by the lambda level formation. And by looking at the distance or the period of this quantum oscillation, you can figure out what is the degeneracy at the Fermi level. For example, at 2 Tesla, different regions shows quantum oscillations, but with different period, right? If you look at here, you see there are 2 features separated by a large charge density. And if you check the numbers, this density corresponds to filling up 4 lambda levels. And that means the degeneracy is completely conserved here. There's no breaking. So we call this as a full metal, degeneracy equals 4. And there are regions where this distance between two adjacent quantum oscillation peaks are separated by a distance that's roughly half of this distance here. That means you only need half of the number of electrons to go from one lambda level to another one. So that corresponds to roughly the half metal. And there are also cases, for example, here, the distance between two features is 1/4 of the full metal. And apparently, that corresponds to only 1 out of the 4 isospin or spin valley copies is occupied. So it is a quarter metal. So by doing quantum oscillation like this, we can get basic idea of what is a degeneracy at the Fermi level. Of course, this doesn't tell you exactly which symmetry is broken. Then you have to do something else to determine whether it's a spin or the valley symmetry is broken. For example, if you have a quarter metal, which means 1 out of the 4 bands are occupied, as we said, this band has large barrier curvature and orbital magnetism. It will naturally give you the spontaneous time versus symmetry breaking, and you get hysteresis in the scan of the Hall resistance versus magnetic field scan. You get a jump, you get a little loop that corresponds to the anomalous Hall effect of that occupied isospin band. And of course, there are cases where the two valleys are balanced, so their anomalous Hall effect will cancel, but they could have the same spin. And in this case, you will have 0 anomalous Hall resistance. And I'm just picking up 2 examples to show you in general how this idea works. There are many different scenarios, more complicated than what I'm showing you. So you can check out the paper by Andrea Young and Stefan Persch at Caltech about such kind of so-called fermiology analysis to figure out the symmetry breaking due to flat band in graphene. And I would like to talk about the specific phase in the diagram that we have got. Here, it's this bubble reside at 0 displacement field, roughly, and it's symmetric about d equals 0, and this is residing on the whole doping side. Okay, in RXX map, it's more resistive than the neighboring state, and we call it the bubble because it looks like a bubble. And as I said, the first thing you can do is to do the quantum oscillation by applying an autoplane magnetic field. And as I said, the periodicity of this quantum oscillation tell you it's roughly a degeneracy of 2 out of 4. So this is close to a half metal. And the next thing you can do is to measure the anomalous Hall resistance. Well, instead of doing magnetic hysteresis, what I'm showing you here is the Hall resistance at 0.5 Tesla. And of course, 0.5 Tesla will give you some normal Hall signal that's proportional to the magnetic field. But those signal is rather small because that corresponds to the color you're seeing here. This is a normal Hall signal. Well, inside the bubble, there's a region that takes the shape of a pair of wings that has much bigger Hall signals, and that corresponds to mostly the anomalous Hall signal. So through this, we know this region is probably a valley symmetry broken metallic state that is close to half metal. So you can further review the orbital magnetic nature of these states. Right? You can park at different points on this diagram and scan the magnetic field. Indeed, you find magnetic hysteresis with a range of jumps in the amplitude and a range of coercive field. So this is an orbital magnet, and the Hall angle of such orbital, this topological metal is pretty big. If you measure the Hall angle by defining Rxy divided by Rxx, it corresponds to a tangent theta of more than 0.6, which is pretty big, and it's bigger than, in fact, anything that I can find in literatures among topological metal. And another way of looking at this magnetic hysteresis is that you have total 4 states that can be switched between. For example, at this positive gate electric field, when you sweep the magnetic field, you are switching both the valley and the orbital magnetization. You go from K prime to K, and remember, these two valleys have orbital magnetization because they are time reversal pair of each other, right? And you can also have the other two polarized states in the K plus M and the K prime minus M when you reverse the sign of your gated electric field. This is when you induce the topological phase transition by closing and reopen the band gap. And there's another effect that we observe is you can look at these wings in different ways. Okay, this is still the pair of wings, but rotated by 90 degrees. This time, instead of scanning the magnetic field, I'm scanning the gate electric field and measure the anomalous Hall resistance here. From left to right and from right to left, you see the color of this anomalous Hall signal is reversed. That means if you do a line cut here at this fixed charge density, you're going to get a butterfly type of hysteresis when you scan the electric field back and forth. So, let me explain to you what this means, okay? You're applying a small magnetic field to prevent the random fluctuation of the small orbital magnet, which tend to happen in this small magnet system. So naively, you would think no matter what displacement field I'm applying using the gate, the external magnetic field will automatically choose the state or choose a value that minimizes the energy, right? M dot B. So no matter I'm at a negative or positive electric field, I should get the same sign of Rxy, which has the same sign as the orbital magnetization. So I should expect an M shape or a W shape when I'm sweeping the electric field back and forth. However, what the system really chooses to do is it doesn't care about the energy of M dot B to some extent. It decides to stay in the same valley as you go across E equals 0, even if this valley K, in this case, is at a slightly higher energy than valley K prime. So in that sense, what's persisting through the scan here is the valley polarization. It stays in the same K valley at the cost of a higher magnetic energy. So there must be some barrier preventing from flipping. And when you get out and jump back in, you'll stay in the other valley, which is K prime, along this line. And you get out, you come back. That is what this butterfly hysteresis is. To be more specific, when you apply a small positive magnetic field, you get this kind of butterfly hysteresis. And it corresponds to a valley hysteresis loop like this. This blue line means you stay in the K valley, and the orange line means you stay in the K prime valley. This butterfly in Rxy corresponds to a hysteresis in the valley polarization. And if you flip the sign of the magnetic field you apply, the direction of winding in this butterfly is reversed, okay? So the hysteresis of valley polarization would change the direction as well. Here is clockwise, here's counterclockwise. And that tells you what really choose the valley polarization is not the electric field, is not the magnetic field, it's a combination of them. Because if you plot valley polarization as a function of E dot B, you can unify the direction of winding of this hysteresis loop. Okay, E dot B selective value. So you can also test this butterfly in different environments, right? For example, you can increase the magnetic field first. As we said, at the small magnetic field, the system decides to stay in the same valley, no matter what the cost of the magnetic energy is. However, if you keep increasing the magnetic field, eventually that M dot B term is going to dominate over everything, and it recovers the M or the W shape as you would expect. So the butterfly is gone. On the other hand, you can warm up your sample and watch how this butterfly evolves. It starts to be like this, occupying almost the whole range of anomalous Hall. But as you warm up the temperature, this butterfly shrinks in the size and eventually disappears at high enough temperature. So we think what's going on here is that you have two states to choose from, polarizing the opposite valley, and there's an energy barrier between them, just like any magnet, right? And you can borrow the two contribution of energy to overcome this barrier. One is the m dot b, magnetic coupling energy. The other is a roughly kBt level thermal excitations. If the sum of them is big enough to overcome the barrier, then the system decides to go from one value to the other one. And that is when the butterfly disappears and the hysteresis is gone. Based on this analysis, you can roughly estimate the orbital magnetization G factor of these electrons, and you find it's on the order of like 20, which is 10 times bigger than the spin G factor of the electron. So orbital magnetic effect in such material could be rather strong because the band gap is small and the barrier curvature is big. From the practical point of view, another way of looking at this butterfly is that you find a way to control the two orders independently. One is the valley polarization, and the other is the orbital magnetization. Because there are total 4 states correspond to the combination of valley and the magnetization. So simply sweeping the electric field, you go around this butterfly, you experience all the 4 states. That means you can use the electric field to independently control the magnetization and the valley polarization. And you can use just one knob to control 2 things. This is even better than what happens in the multifluidics, where you can use electric field to control magnetism or use magnetic field to control electrical polarization. Here, you can use one knob called the electric field to control 2 orders independently. Okay. So the bubble is a specific example of valley symmetry breaking. And there's some anomalous Hall, but it's not quantized yet. Okay. So next I'm going to show you is how we can make this anomalous Hall signal quantized. So we observe the integer quantum anomalous Hall effect. A very brief review of integer quantum anomalous Hall effect. It's an analog of integer quantum Hall effect, but at the zero magnetic field. And people were all enlightened by Duncan's theory proposal in 1988, where you assign the right hopping parameters for electrons on this graphene lattice. You can eventually realize such a state where you get quantized RXY at the zero magnetic field. Experimentally, it was first observed in magnetic topological insulators, where you get RXY quantized as h over e squared, which corresponds to a Chern number equals 1. This happens at tens of millikelvin range. And after that, there has been several systems where people also observed integer quantum anomalous Hall effect in more intrinsic magnetic TI, or in 2D Moiré superlattices between graphene and graphene, HBN, or between 2 types of TMD. The common feature shared by all these systems is a Chern number equals 1. RXY is always h over e squared. And let me show you how we can get quantum anomalous Hall in our system and the journey of we got there, because it's not something we got in the very first place. So it all starts from this observation of this correlated insulator at displacement field equals 0. That is corresponding to the correlation effect of flat band gap out the band structure, so you get the insulator. When you apply bigger displacement field, you can drive the transition from correlated insulator to a metal to a banded insulator. And another evidence of this state being a correlated insulator is if you do the thermal activation measurements, you warm up the sample, and you just monitor the resistance in this correlated insulator and a banded insulator. You see that the correlated insulator start to be much more resistive than the banded insulator at the lowest temperature. However, as you warm up, this state at d equals 0 quickly drop in resistance and eventually become several times more conducting than the state at the high displacement field. If you believe this high displacement field part is a banded insulator, that tells you the gap in this correlated insulator state is shrinking by itself as you warm up. And that is a typical signature of a band gap due to electron correlation. Okay? If you warm up to high enough temperature, the state here at d equals 0, you cannot even tell that is an insulator state because it becomes even more metallic than the metallic state in the intermediate D. And when we apply magnetic field, we still look at this phase transition from D equals 0 to high displacement field. In this region where we think it has band gap closed and become a metal or semi-metal, in magnetic field of 2 Tesla, we observe some feature that seems to be quite obvious and dominating over all other features. It is happening at a charge density close to 0, but not exactly 0. And the Rxx goes to almost 0 there. So we did further analysis of that state, okay, this state here. And this case, I'm plotting the ND map, okay? This is taken at 1 Tesla. This little dot here is what you were looking at here. This happens at a finite charge density, but the displacement field in the middle of that phase transition. You can see, as a function of charge density, this state here corresponds to Rxy quantized at h/5 squared, and the Rxx almost vanishes. So you got 2 options. One is this is an integer quantum Hall effect because there's magnetic field. But the other one is this is a Chern insulator that does not need magnetic field, but somehow gets stabilized by magnetic field, right? We think at that point we can already claim the state as a Chern number equals 5 integer, a Chern insulator, because these are the features correspond to the lambda levels or the quantum Hall. They are much weaker. They are far from being quantized. While this state here, c equals 5, is perfect quantized as soon as it emerged at 1 Tesla. So we think this is enough to support that this state is a Chern insulator. And it has a right slope following the Strata formula. But apparently, it doesn't persist with 0 magnetic field. And if it's a Chern insulator, in principle, you don't need magnetic field. So we have been thinking about ways to try to stabilize it at 0 magnetic field. And eventually, we figure out a way, which is to borrow some spin-off coupling from the neighboring WS2 layer. WS2 is a semiconductor TMD. It has very strong spin-off coupling. So when you put it next to the 5-layer rhombohedral graphene, the electrons in graphene can experience that spin-off coupling, and that turns out to be the key ingredient to stabilize the c equals 5 state at the 0 magnetic field. Okay, first let me show you the data. You play the same trick. You apply charge density and displacement field, and you see this region used to be that semi-metallic region during the phase transition from correlated insulator to a band insulator. Now you get a big anomalous Hall signal here, and you get almost vanishing Rxx. And if you park at the middle of this region and sweep the magnetic field, you get the right magnetic hysteresis loop of Rxy that corresponds to h/5 squared. It is 5 times smaller than h/5 squared, than h/e squared, and that tells you it's a Chern number equals 5 state. So experimentally, this is a recipe you can get a high Chern number integer quantum anomalous Hall effect. And then we start to think about, in the whole picture, what's going on here. And it turns out we have a toy model to explain roughly what's going on, although it was not predicted. So we think it has a lot to do what's going on at d equals 0. Although d equals 0 state itself is not topological. It's an insulator, it has no anomalous Hall, but it is a key ingredient here. So this instability of band structure at the band touching point was discussed heavily, even in the case of bilayer graphene, when the band dispersion is not as flat as k to the 5th. Even in the parabolic band dispersion, people discuss this instability under electron interactions, and they identify a specific state called the layer antiferromagnet state as the possible ground state there. Or the layer antiferromagnet means spin up electrons in both k and k prime valley. Here the color corresponds to the valley. Both the k and k prime spin up electron occupy the top layer of graphene, and the spin down counterparts occupy the bottom layer. So they are spatially separated. Temperature symmetry is already broken in this sense, but it has a 0 anomalous Hall because you still have the balanced valley distribution. K and k prime still cancel each other. However, if you start from that layer antiferromagnetic state and you apply a displacement field, something interesting could happen. Because now your spin has a layer polarization. Applying the same displacement field will change the band gap of spin up and spin down band structures in different ways. It will enlarge the band gap in the spin down band gap, and it will make the band gap of spin up smaller due to this extra electrostatic potential due to gating. So you can temporarily forget about the spin down copies of the band because we only care about the low energy band structure. And in this case, you still have the K and the K prime valley degeneracy still remains there, and they will still cancel each other to give you a zero Hall resistance. And that is a moment where we need the spin optocoupling from the neighboring WS2 layer, which will break the K and the K prime degeneracy corresponding to the same spin through this Ising form of spin optocoupling. As a result, we can make the band gap differently for K and K prime of the same spin, and we just massage the displacement field a little bit. We can close the K prime band gap and reopen it. When that happens, the Chern number or the barrier curvature of the conduction and valence band is swapped. So I have eventually a state like this, where both the K and the K prime value have the same sign of barrier curvature, and they will add up to give you that C+5 state. Okay, it's rather involved, but I just want to show you experimentally how we went through the journey. We didn't come up with this idea, but that observation of C+5 Chern insulator at 1 Tesla intrigued us to think about how to realize integer quantum anomalous Hall system, and it indeed works. I want to speak a little more about the comparison of this C+5 integer quantum anomalous Hall with the observed C+1 quantum anomalous Hall in other systems. Okay, first of all, our system has no magnetic element in it, which means this is different from the spin order case in the magnetic TIs. Yes?
It's from 5 layer.
It's from 5 layer, yes.
So for the 3 or 4 layer, you expect to get 3 or 4.
No. I mean, ideally, if this picture persists, it should be 3 or 4, but nobody has observed quantum anomalous Hall effect in 3 or 4 layers. There's some subtleties that I'll be happy to tell you later. Yeah. So apparently, our case is different. It's a different magnetism from the magnetic TI. It doesn't rely on the ordering of spin of magnetic elements. And it's also very different from the quantum anomalous Hall effect observed in 2D Morée superlattices. If you're familiar with the literature, what happens in the Morée superlattice is that you get this Morée mini bands that carries Chern number, opposite value of K and K prime carries the opposite Chern number. However, if you put the right amount of charge to occupy only one of the band, the exchange interaction tends to force the electrons to stay in the same value. So when you are at the exactly odd filling factor of the Morée superlattice or the Morée band, you're going to harvest the Chern number of a specific value, and that is how you break time versus symmetry. Well, if you remember, in our case, the states of C+5 happens at charge neutrality, which means it is different from the Morée superlattice. It happens when the two values of K and K prime are equally populated, but they have opposite band gap, which is exactly what you get from the Haldane model, where you have the band gap of one value is inverted, so the two values no longer cancel, instead they add up. So we think through this toy model, we realize the Haldane model by borrowing several ingredients: correlation of flat band, gate tuning of displacement field, and the spin optocoupling from the neighboring WS2 layer. And that's how we can make this anomalous Hall effect quantized. Let me see how I'm doing on time. Oops. Okay, maybe 15 more minutes. So the last topic I want to talk about in the absence of Morée superlattice is superconductivity, which is a very important topic in condensed matter physics, in correlation physics. And here's a little background. As I was telling you, there has been superconductivity observed in graphene in various systems by various groups. The first one is in the magic angle twisted bilayer graphene. You get superconductors, you get multi-insulators, and this phase diagram really reminds you of what the phase diagram of a high TC superconductor looks like. And that's why people were very interested in studying this magic angle bilayer graphene as a platform to understand the superconductivity in other condensed matter systems. And later it was shown by Andrea Young that even in the absence of twist angle or moire, you just have a trilayer graphene in the ABC or rhombohedral stacking order. They also observed the superconductivity they name as SC1 and SC2. Although these superconductivity happen at a much lower temperature, about 1 order magnitude at least, than the superconductivity in magic angle bilayer graphene, but they are superconductors, okay? And later they found you can also get superconductivity in AB stacked bilayer graphene if you put it in an in-plane magnetic field. After that, there are works done by Stefan Noah-Perch group at Caltech, where they found that by introducing the WSE2, which is again a semiconductor TMD with strong spin-off coupling, you can stabilize superconductivity in both the non-twisted and the twisted graphene system. So in general, spin-off coupling seems to be good for superconductivity. It either induces superconductivity in the part of the phase diagram that is not superconducting without TMD, or it makes the superconducting transition temperature significantly higher than without the TMD. And in general, people find superconductivities at the phase boundaries of some symmetry breaking transitions. For example, this SC1 here is along a boundary where the isospin polarization changes. So I want to show you our effort in this direction. So we have a device where we put this ABC trilayer graphene in the rhombohedral stacking order, neighbored by WS2 layers. We found almost no difference between WS2 and WSE2 in this case. The key point is that we now introduce some spin-off coupling. And again, we can control the charge density, we can control the displacement field, and ask what is the ground state of the sample. As you can see here, dark blue color means the resistance is 0. And we did observe 4 regions that have 0 resistance and correspond to the superconducting state. One is what we call as SC3. The other is what we call as SC4. It's mirror symmetric about D equals 0 because we have WS2 on both the top and the bottom of this trilayer graphene. So no matter you polarize the electron to the top layer or the bottom layer of the trilayer graphene, they both experience strong spin-off coupling. So both SC3 and SC4 are mirror symmetric about D equals 0. At the same time, and this SC4 is completely absent from Andrea's previous data where there's no TMD. And SC3 is sort of there, but it's very weak without TMD. And what's interesting to note is that the originally observed SC1, which is supposed to be here at this phase boundary, seems to be absent when you have spin-off coupling. So let me show you this, one by one in more detail. Okay. First of all, to show that it is indeed superconductivity, you see the sharp transition of resistance as a function of temperature in SC3 and SC4. You see these peaks in the differential resistance as a function of current. So these are the signature of superconductivity. First, let's look at the SC4, which is a completely new superconducting state that was not there in the pristine form of ABC trilayer graphene. We have actually 2 devices that tells us exactly how this works continuously. So we have a device where the ABC trilayer graphene is neighbored by just 1 layer of TMD. And when we apply the electric field to push the holes or the charges to the layer that's far away from the TMD, you can pretty much think about that as there's no SOC, there's no spin-off coupling because these electrons are far away from the TMD. In that case, this region doesn't show zero resistance. So superconductivity is not there. That's consistent with Andrea's previous report. And we have the same device, but we can change the displacement field sign. We can now push these holes to the layer of graphene that's right next to the TMD. Now they can feel some spin-off coupling. And the observation is that it shows some small difference. Right now, there's a little blob here that is slightly more bluish than the neighboring region, and that is absent from here. So this is when you have some weak spin-off coupling, the system is going that way, although it's not completely stabilized, but it is on the right direction. And when you check the other device, which you have WS2 from both sides, no matter which side you put your electrons, you got very well-defined superconducting state. So it feels like in this case of SC4, spin-off coupling can induce superconductivity that is aligned with what Stefan was reporting in both twisted and non-twisted graphene system. And this superconductivity resides at the boundary of isospin phase transitions. And how you can tell that is you can do a vertical line cut here at constant charge density, but a range of displacement field. What you find is that, again, when you apply magnetic field out of plane, you get quantum oscillations, right? The period of the quantum oscillation will tell you the Fermi surface degeneracy and some information about the size of the pocket you have in different flavors of spin and valley. So you can do this quantum oscillation map like this, and you do Fourier transform using magnetic field as a parameter. Then you can get, on one hand of the superconducting state, there's very well-defined features corresponding to the half metal, which is corresponding to 2 out of the 4 isospin copies occupied. And to the right of the superconducting state, you see features that's somewhat similar to the half metal, because there are also features this way at half, the right period for the half metal. But there's also features at small frequencies. And eventually, we think this is how the Fermi surface look like. In addition to the big 2 pocket, you have 2 small pockets in the other 2 flavors. And the superconductivity happens at the boundary between these 2 phases. More analysis here, right? This is SC4. It can persist to an outer plane field, magnetic field of roughly 20 millitesla, which is very typical for graphene superconductivity. And if you apply an in-plane magnetic field, this superconducting state shows a Pauli limit violation of a factor roughly up to 3. Because there is spin-off coupling in the icing type, the spin is sort of locked to the outer plane direction. So when you apply in-plane direction magnetic field, it is hard to destroy superconductivity, and that's just why there is a Pauli limit violation. Okay, so everything here in SC4 seems to agree with what people have discussed previously. Next, this SC3 is somewhat a new observation. Again, in the device where you push the electrons to the layer away from the TMD, it experiences negligible spin-off coupling. There's almost no well-defined superconducting state, although there is a very shallow dip in the resistance. And this is also seen in Andrea Young's student's thesis, although this was never formally published, but we dug out that from his thesis, so this is consistent. And what's different now is that if you push the electrons to the layers that's right next to the TMD so they can experience spin-off coupling, somewhat weak spin-off coupling, you now have a region roughly at the same place at these dips that shows resistance down to 0. And if you make the spin-off coupling stronger, this region shows superconductivity becomes bigger, although it doesn't look exactly the same shape, but it is expanding. So we think this is a state of superconductivity that got enhanced by spin-off coupling a lot. And similarly, this superconducting state also happened at the boundary of some isospin phase transition. For example, as you look at here, this region here has the right periodicity of quantum oscillation corresponding to a half metal. And to the very right, there are features, although split up, but around 1/3 frequency. And that corresponds to roughly a 3/4 metal, means 3 out of the 4 isospin copies occupy, but maybe one of them is slightly different in exact size from the other two. That's why there is a splitting. And superconductivity happens in between them. Again, this is still aligned with the picture that superconductivity happens at phase boundaries of some isospin symmetry breaking transition. And lastly, I want to talk about SC1, because SC1 was thought to be the simplest superconductivity observed in trilayer graphene. There's no polylimit violation. It's just, everything looks like it's a simple S-wave superconductor. And what we found is that when you have strong enough spin-optical coupling, this SC1 state got completely killed. Okay, and this also happens in a gradual way. This is the sample where the holes are away from TMD. So you can think of this as pretty much pristine ABC trilayer graphene without spin-optical coupling effect. And you can actually see this blue stripe here that corresponds to the superconducting state SC1. When you push these holes towards TMD, you introduce some weak spin-optical coupling. The superconducting state is still there, but now it has a slightly lower transition temperature than far away from TMD. Okay, so it's disappearing, but it can still go to, a low resistance state. However, if you increase the spin-optical coupling even more, as in this device, the superconducting state SC1 is completely gone. This is a bit puzzling because spin-optical coupling, icing type still preserve time-residual symmetry, right? In the simple picture, it should not keep, it should not kill a simple S-wave superconductor where the two core pairs of opposite spin, right? So we do not really understand what's going on, but we believe this is against the common wisdom accumulated in the past few years that spin-optical coupling always enhance or strengthen superconductivity in graphene system. This is a counter example. So through this 3 superconducting state, you can see there's a mixed role of what spin-optical coupling does. For some of the state, it enhances superconductivity. Some of the state, it induces superconductivity out of nowhere. And some of the state, it even kills already existing superconductivity. All these superconducting states reside at some phase boundary of isospin symmetry breaking and phase transitions. So I think this is pointing to more experimental and theory efforts to understand exactly what are the mechanisms of superconductivity in this graphene system. And this is an ongoing effort in many groups, including ours. So with that, I would like to wrap up my session 1, which focus on the correlation topological effect in crystalline multilayer rhombohedral graphene in the absence of Moiré effect. And next, we're going to march into the realm where Moiré is playing a critical role. So with that, I think it's time to make a pause here.
Yeah, thanks for showing all this nice data. So coming back, I think, to section number 2, where you showed this butterfly shape, can you say something about domains? Because you said the signal is very strong, right? But then on the other hand, you were showing that it's kind of hard to spin polarize it with an external field. So I would think typically you would have many domains in such a scenario, right?
Okay, so you actually have pretty much just one domain, we believe, in this case, because whenever it changes, the RxY changes, it jumps to the opposite value, roughly, instead of showing several small steps of changing, right? And experimentally, we did observe this when we train the sample when the temperature is high. We apply a magnetic field, we field cool it. We train the sample, so it's likely to kill the domains at that stage already. And if we just do random cool down without magnetic field training, we don't have butterfly hysteresis like this. It's much more complicated. And that is the signature we believe there are small domains if you don't train properly.
Yeah, you mentioned you observe the sigma xy to 5 infinite quantum Hall states, maybe around 1 Tesla. I wonder whether in the stronger field, you still see that in which range magnetic field it is.
I don't remember exactly how high a field we got, but the field Tesla, I think, is still there. But as you apply higher and higher magnetic field, the lambda levels got promoted also. And there may be some critical field that you cannot distinguish this equals 5 transmitter from the other,
Because you mentioned this one is from this direct node, this fun inversion. But in the very strong magnetic field, the magnetic energy is comparable to this whole flat band energy. Then things may change. I wonder when you see this change.
Yeah, I would say it's probably on the order of like 7 or 8 Tesla. They start to be smeared somewhat equally. Yes.
The last bit, so you considered Ising spin order coupling, right? But at the interface, inversion is broken, I assume, right? So couldn't you also have Rashba type terms?
That's even more complicated.
Yeah, so in the last part in the superconductivity, where you were comparing I think this was SC1, you were showing the 3 different samples. And so in,
Two different samples.
Sorry, 2 different samples, 3 different scenarios. Yes.
Yes.
And you also showed a DVDI, yeah, this one. So I'm looking at the lower left here. Should I take seriously that the blue trace has kind of a higher critical current, but has a lower critical temperature? Possible details specific to the sample.
To be honest, I do not know. I mean, these two are the same samples, just the opposite displacement field. That's a good question. I mean, yeah, the short answer is I don't know. Other questions? Yes.
Yeah, just curious. Do we have an estimate for what the ratio of the bandwidth to the interaction energy is in the rhombohedral case?
Okay. In the case of no moire, the band is continuous, right? So you have to be specific about what bandwidth we're talking about. I think if you look at the band structure calculation based on type banding, that the really flat region that has some up and down, in the pentalayers graphene case, I think it's roughly in the range of probably 5 millieV or smaller than that. Yes. Oops. Too much. Yeah. So if you look at this part, is roughly 5 millieV with some like Mexican hat, trigonal warping of the band structure. That's roughly the flat part. And the interaction energy scale, I mean, you have to find a characteristic length. In the case of moire, roughly if you have a moire period of something like 15 nanometers, the simple E squared over L estimate give you something like 25 millieV. So it could be strong. It could be like, kinetic energy is well below the interaction. Or it could be comparable. Yeah.
Other questions? No? So let's thank Professor